Okay, let's get started. Yeah, sorry for the interruption. Okay, so let's discuss what we covered in our last lecture. So in our last lecture, we continue talking about chapter 9. So we go over the converse proof of the capacity of AWGN channel, and then we go over the capacity of other channels, right? So we give some examples for a few of them, right? So we consider the non-Gaussian channel, right? And we consider the band-limited channel, right? And today we're going to see some other kind of channels. Okay, and here are some definitions for the AWGN channel. And we know the capacity is given by this formula, right? So here the constraint is the power, right? So remember that we have this power constraint. Yeah, it should be average power. There should be 1 over n in front. And in our last lecture, we went over the converse proof, right? So we went over the typical 5 steps, right? So here, it's almost exactly the same as before, right? So the only difference here is that we're starting from the discrete entropy, right? And then, so we get the mutual information, and then we expand the mutual information in another way. So here we get the differential entropy, right? So that's the difference. And the other difference is that we need to take care of the power constraint, right? That's how we got this log formula. Okay, just be careful on that. But the idea is exactly the same as before. So we have been seeing this for like maybe the 3rd time in this context, but the 4th time overall. Okay, so and here is some geometry interpretation of the channel capacity. So basically, you consider this sphere is what we can receive. Okay, and the radius of it is square root of p plus n, right? Remember that? And then, so this is a total, total space that, we can receive, right? And then, so each small sphere represents a transmitted code word, x, right? Therefore, since the power of each x is p, so the radius of this is square root of p, okay? So the channel capacity basically means that, in this kind of sphere, so in total, how many number of small spheres can be fit, okay? So that's called sphere packing. Okay, and in the distortion that we're going to see from today, so we have the opposite of it. It's called sphere covering. Okay, so basically for the source coding problem is that okay, so now the whole sphere is not it's not the received space in the channel, right? It's our source code, source information. Okay, and then we need to design some sphere to cover those. Okay, so that's another problem. All right, and then we start talking about the capacity of some other channels. That we start with the non-Gaussian channel, right here. So the conclusion is that okay, so if the noise z is not a Gaussian distribution, right, then the capacity of this kind of channel will be higher than this, will be higher than the Gaussian channel. Okay. Remember, and we give a proof of that. And when I review my notes, it turns out that there's a problem in the proof I gave in class. Okay, so do you see the problem? So there's a mistake here. Right, yeah, let me tell you the mistake. So basically, the mistake is basically here. Right, so we cannot make y as a Gaussian distribution because the only thing we can control is x. Okay, so or it's hard, right? We cannot guarantee that we can make a distribution like that, right? So this step is not valid. We need to remove it. But it still works, right? The reason is that, so now for this guy, for this entropy, right, we use entropy power inequality. So we use that guy, and then we can still get it. Okay, so it doesn't matter too much, but here, we need to be a bit more careful on the entropy power, on this step, right? So we cannot make a distribution of y. Okay, is that clear? Let's be careful on that, okay? All right, so let me see. Yeah, let's go back. So in the video, everything is correct, right? So if you're confused, just look at the video. So because I can edit, right? So I just remove the part I don't want, and then I can, stick everything I want all together. So in the video, it's perfect, but in the class, it's wrong. Okay, just don't get confused, right? Okay, so next we go over the capacity of band-limited channel, and for here, so here we connect the capacity per channel use to the actual number of bits we can transmit per second in practice. Okay, and here the problem we consider is that so now the practical channel, or it's either a wireline channel or wireless channel, so we have a limited bandwidth. Okay, and this is how the channel look like. Okay, and N naught here, so this is the PSD of the noise, right? So therefore here the connection between a real channel and our discrete so the channel we consider is still discrete, right? So the continuous part here we talk about is the value of the code word, so and the value of the noise, right? They are continuous, but for the system it's still discrete time system, okay? And so the way to connect from continuous time system to discrete time system is via sampling, okay? And here what we do is that we use a Nyquist sampling theorem, okay? So then we can have a bunch of samples, okay? And that is the connection here, okay? So we need to use the Nyquist sampling theorem with the sampling frequency of 2 times W, where W is the bandwidth. Here W is basically this, right? The negative part doesn't count, only the positive part, okay? So, and therefore, in this way, we know that every second we have 2 W samples, right? Means that we have 2 W channel uses, right? Every sample is a channel use, okay? And for each channel use, we can have a capacity of the half times log 1 plus signal to noise ratio, okay? And then times W and so on, then we can have this, okay? So basically, this is what we got, okay? So this is the capacity for the band limited channel. And we can see that the bandwidth appear here and the bandwidth appear here, okay? And this is the real power of the signal, meaning the watts per second, okay? Therefore, for each channel U, the power would be Px divided by 2W because we have 2W samples per second, okay? So this is bit per second, okay? And we analyze this capacity formula for 2 regimes. One regime is called band limited regime, so which means that the power goes to infinity, right? But the bandwidth doesn't change, okay? That's why it's called band limited, right? Because we have limited bandwidth, and this will be the capacity, right? You can see that, okay, here, so if Ps goes to infinity, then the capacity can go to infinity, which is good, okay? And for the other regime, it's a power limited regime, right? Which means that the bandwidth can go to infinity, but power is limited, right? In this regime, so when the bandwidth goes to infinity, we can have the capacity equals to Px over N naught times a constant here. Okay, basically capacity equals to SNR, right? And here you can see it's not scalable with the memory, right? When memory goes to large, the capacity will convert to a constant, right? The reason is that we have the bandwidth both here and here, okay? So, and in practice for the UWB communication, ultra wideband communication, so it falls in this regime, right? But for cellular, for Wi-Fi, right, we're in this band normally, in this regime. Okay, and questions? Oh, and the other thing is that normally in practice, you may see this formula a lot, okay, without this W. So basically, in practice, we normally normalize it by time and by the bandwidth, right? So it's called spectral efficiency, okay? So it's number of bits per second per hertz, right? Because in practice for communication, we have 2 resources to use. One resource is the time, and the other resource is the frequency, okay? So they're related, they're not unrelated, okay? But we have 2 resources to consider. Therefore, in practice, normally we consider a bit per second per hertz, okay? So, and then we move to the parallel Gaussian channel. And for the parallel Gaussian channel, it's very similar as before, but the only difference here is that, so we consider a bunch of them, right? Before we have done y equals to x plus z, but here we consider a bunch of them, right? There are different channels, right? So this n is not a block length. It's not a code length, right? Don't get confused, okay? It's the number of channels, okay? So now we have n channels. So the difference compared to before is that now we have a total power constraint, right? So if a sum of the power for all of the channels, then it has to be less than or equal to p, right? Before, so we have pi. For each individual one, so it has to be less than pi. So here should be less than or equal to pi. But for the summation of them, here now is less than or equal to pi, okay? So this basically means that we have the possibility to allocate the power for each channel, right? Ideally, if the channel is good, we want to allocate more power. If the channel is bad, we want to allocate less power, right? Because if the channel is bad, then why do we want to use it anyway, right? So that's basic idea. Therefore, we can formulate this problem, right? So basically, what we should do here is that we summation over all over the mutual information, right? And then we have the power constraint, right? We want to maximize this problem, solve this maximization problem, and eventually, so this is what we're going to solve. Okay, does it make sense? Okay, and you can derive it. It's very easy to derive, so it's very similar as before. Okay, so now let's see. Let's see what we're going to cover for today. So today we're going to finish talking about our chapter 9. So first, we'll finish talking about the capacity of parallel Gaussian channel. Okay, and then we'll start talking about our chapter 10, so which is the last chapter in our class. Okay, so we'll not cover anything further than chapter 10. Okay, and so chapter 10 is about, we're going back to source coding again. Okay, so before we talk about the lossless source coding, which means that we have to recover the source information exactly, right? But here, so we allow, there's a mistake. We allow the loss there. Okay, so lossy source coding. So first of all, we're going to talk about the quantization. Okay, and then we'll talk about the rate distortion theorem. Yeah, distortion basically means the loss. Okay, so that's the agenda. Okay, first, let's take a look at how can we solve the capacity of the parallel Gaussian channel problem, right? So here, as we said before, so we have a power allocation. So we convert the problem from a to a power allocation problem. Okay, so basically what we want to do is that we want to maximize the summation of the capacity of all the channel. So we assume that the PSD is different for each channel here, okay? So we have Ni for, so that means that the noise power spectrum density for each Gaussian channel, and subject to the summation of all the power, so that has to be less than P, okay? And we also have the constraint Pi is bigger than or equal to 0 for all I, okay? And clearly, so this is optimization problem, right? It's a constraint optimization problem, and we know, we can see that, so this problem is actually a convex optimization problem. Okay, so basically, so we can show that, so all of the functions here are convex function or convex concave, right? So because we're doing maximization, so this has to be concave, okay? And all the functions here are convex, okay? And therefore you can show it is a convex optimization problem, okay? So any question here? Okay, then, we know how to solve a convex optimization problem, right? So before we have seen how to solve that in general for the discrete memoryless channel. Right there, we just do the derivative. We write the Lagrangian multiplier formula, right? And then we do a derivative of that with respect to px at that time, right? But here, we just need to do the derivative with power because the only variable here is the power, okay? So that is what we're going to do. Okay, first we need to write the Lagrangian function first. Okay, so basically we're going to write the Lagrangian function and then we use the KKT condition. Okay. So the nice thing here is that we can get very nice interpretation for the solution if we use the KKT condition. Okay. So we're gonna write the first one, the objective formula. Okay. And then we can add or minus, doesn't matter, for the constraint here. Okay, so in this case, because we're using plus, then lambda has to be less than or equal to 0. If we use minus, then lambda has to be bigger than or equal to 0. And then we need to add another term, but it doesn't matter because, so for this term, we can deal with that easily because, yeah, we can just deal with that easily. So yeah, we don't need that. Okay, for the KKT condition. Okay, so if you don't remember the KKT condition, so it doesn't matter. So as long as you know, okay, you need to write the objective function and then add the Lagrangian multiplier, multiply this constraint, I think it'll be okay, right? Because now the only thing you need to do is to maximize the whole thing. Okay, so for the KKT condition, it basically tells you that, okay, so there exists some lambda such that, when you pick the right lambda, so the optimal value of this guy will be the same as the optimal value of this guy. So basically means that, so this guy has to be 0. Okay, either lambda is equal to 0 or either this equals 0. Okay, so don't remember KT condition doesn't matter, just try to optimize it, right? How can we optimize it? We have two conditions, right? So if PI, here I'm talking in a kind of intuitive way, right? You can, exactly follow the KKT condition, write everything down and solve it. It's totally okay. Yeah, but it's kind of boring, just writing down the formula. So here is, we can do that in a more intuitive way, right? So let's say, okay, when we solve this guy, because we have another condition, so this guy we didn't incorporate here, right? We can do that without any problem, but we don't need to do. So basically, we have two conditions to consider here. So one is that when pi is bigger than 0, right? When the optimal pi is actually bigger than 0, then the derivative has to equal to 0 because this is achievable, right? So then the derivative of this guy, log 1 plus pi over ni, and add lambda because we do a derivative with pi here, right? So this has to be equal to 0, right? Because that can be achieved. Okay, so then we don't have any problem here otherwise. So means that pi equal to 0, right? Because pi is either bigger than 0 or equal to 0. Okay, when pi is equal to 0, clearly, the optimal value should be what? Pi is less than 0, right? So it will be something like this. Okay, so this is the optimal. Well, so there will be some. Come on. So there will be some value here, but it's less than 0, so it cannot be achieved, right? So which we do not want. Therefore, we have to take the optimal value here, right? In this case, you can see, the slope here is definitely less than 0, right? Therefore, we can show that in this case, this guy, right? And then I don't write it here, so just move it here. Plus lambda will be less than or equal to 0. Okay, so we have two cases to consider here. Okay, you can see that for some pi it has to be equal to 0, and for some pi it will be bigger than 0. Okay, so now let's talk about this. So let's compute this guy. Okay, so yeah, after some manipulation, you can see. So this means this guy, 1 over ni, and then 1 plus pi over ni plus lambda. So this is equal to 0. Okay, if you compute the derivative explicitly, then you can get this, right? And here we take the log, based on e for simplicity. Okay. So it doesn't matter. So this guy equal to 0, right? And then from here, we can solve it. So basically it means that ni plus pi equals to minus 1 over 2 lambda. Okay? So here we just, because lambda is just a constant, right? So it's a Lagrangian multiplier, a constant here, so it doesn't matter the form of it, right? So and the lambda is less than or equal to 0, so this kind of makes sense, okay? Because this plus that has to be bigger than 0. Okay, so we just give a new name here. We assume that is mu. It's nu. Okay, so this guy equals to nu. Therefore, we have our solution, right? So basically, it means that so ni plus pi has to equals to nu or pi equal to 0. Okay, when pi equal to 0, so it basically means that this guy is less than 0. And when this guy is less than 0, means this is less than 0. Okay, when this is less than 0, it basically means that so ni has to be bigger than or equal to nu. Okay, you can verify that'll be true. Okay, therefore we can get the optimal pi, right? The optimal pi would be nothing but the maximum of nu minus ni and 0. Okay, so if nu is less than ni, then it will be a negative number, so we're going to pick 0. Okay, so that's basically the solution here. Okay, but the next question is that nu is related to the Lagrangian multiplier, right? And we don't know that, right? The next question is how can we determine nu? Yeah, how can we determine the exact value of this guy? Any idea? You remember, so when this is true, it basically means that the pi is bigger than 0, right? So we have a condition that can be used here. So we have this condition, right? So basically, if we sum over all the pi that's not 0, so this would be equals to p, right? Because we have the KKT condition. It tells you that either this is 0 or this is 0. And when we pick p equal to this guy, clearly lambda cannot be 0. Otherwise, nu will be infinity, right? Therefore, so this condition has to be active, okay? Therefore, so we can determine nu according to this guy, right? If we sum over all the power that is not 0, then this has to equal to p, right? And from here, we can get nu. That makes sense? Right? Is the logic clear? Okay, great. So let's see what does that mean exactly, right? So now nu is a constant. We can determine that using this formula. So nu is a function of p and ni, right? So this basically means that if nu is bigger than ni, then we're going to use the power of nu minus ni. Otherwise, it is 0. The power is 0, okay? So if you want to sketch it, so it is like this, okay? So let's say here is the index of the channel. Let's say maybe you have the channel 1, channel 2, channel 3, channel 4, channel 5, okay? And let's say the y-axis is a power allocation. No, y is not power allocation. So yeah, let's say just some value here for y, okay? Or let's say it represents the power level somehow. Let's say it's some power level, but it's not power allocation. Let's say here for the first channel, right? Let's say this is the value of N1, okay? And for the second channel, let's say this is value of N2, is the noise variance. And for the third channel, so this is value of N3. And for the fourth guy, so this is value of N4. And let's say this is value of N5. So this basically means that the first channel is pretty good, second channel is even better, the third channel is really bad because noise is very powerful, it has a high power. And channel 4 is okay, and channel 5 is pretty bad. Okay, so basically this formula tells you that, okay, we're going to determine a nu like this. Let's say here is the value of nu. Okay, so now what we're going to do is as follows. So basically this is nu minus N1, right? So then that's so this is P1, okay? And for the second one, so this is nu minus N2, right? So this triangle, the shaded area is P2, okay? But for the third one, so n minus n3 is negative, okay? Therefore, so P3 is 0, right? Anything above this bar, so we do not allocate any power. And for this guy, we know P4, oh no. No, P4, this is P4, and for P5, it'll be 0. That makes sense? Okay, so now, so this is basically a sketch, okay? So it's like, okay, so now we have a bar here, okay? And then, here's the bottom is not even, but after, the power location, so everything is even. So what does that look like? So if you consider, this as a bowl, and then we pour water into it until the water is even, okay? So this is called water filling algorithm. Yeah, did you heard of it?
I think it's a leak code question. I remember solving that one time.
Solving what?
It's like an interview question for coding.
Oh, leak code question, yeah, probably, yeah. So yeah, this is called water filling algorithm, water filling principle, right? So basically it's kind of pouring water there, okay? So, and so we have a lot of application in practice, right? So now you may be wondering, okay, so is this model a realistic model, right? This is a parallel Gaussian channel is a realistic model, right? So there are a few, things because, now the noise has to be independent, right, with each other and so on. So actually it is very realistic. So we have applications today everywhere. Okay, so when we consider a channel with intersymbol interference, yeah, which means that when the signal transmits over the wire, so the symbol, the symbol will interfere for other symbols, every symbol. Okay, so for this kind of model, it's called frequency variant model. Okay, so the solution for this guy is that, so in the time domain, so if we want to transmit the sequence of symbols in the time domain, the symbol will mix together. Okay, but in the frequency domain, so we're gonna have something very nice. Okay, so we covered a little bit that in the communication class. So basically what we're going to use is as follows. So basically in the frequency domain, okay, so if we transmit a rectangle wave in the time domain, then in the frequency, what it will look like. Right, if in the time domain it's a rectangle, in the frequency that will be a sink, right? So it will be basically like this. Okay, very nice. So this is a frequency domain, so we'll have F here. Okay, so but this is just a rectangle, right? If we times a phase in the time domain, so if in the time domain we do a phase shift, multiply e to the power of j whatever, and then in the frequency domain that will be a frequency shift. Very good, right? So therefore, so if let's say if you transmit two this kind of signal altogether, so one without phase shift and the other one with a phase shift in the frequency, it will be like this, okay? And then if we can pick a nice shift here, so we can make it exactly like this. You can see the point here is that, it has to pass this point, right? So it basically means that, if we take this point out, there's no interference, right? If take this point out, there's no interference, right? Let's, consider this would be exactly the zero crossing point, right? If we keep doing, we can add a bunch of them together, right? So we can have another one here. Okay, so I have to draw this extremely carefully. And something like that. And then when I take this out, there's no interference. right? So this point can be exactly in the zero crossing point, right? And you can imagine that, this is called, so did you see this before? Yes, what are they called? OFDM. So that is what we use in Wi-Fi, 5G, everywhere you can imagine. So it's orthogonal frequency division multiplexing. Okay, you can see, so this is called orthogonal, right? Okay, and if you have this, okay, but here the transmitted signal, right? So we need to multiply that by a channel on top of it, right? Therefore, so this kind of channel will be a parallel Gaussian channel, right? So then this is a way to deal with the interference, intersymbol interference, right? So here in the frequency domain, it's all independent, it's parallel, right? There's no any interference because we have this zero crossing point, okay? So this is how we use the water filling, because now, so we can allocate, so for each channel, they can be independent, and we can allocate the power to maximize the capacity, okay? And this is what we use in practice, okay? And the last thing is that, okay, so what if the Z are not ID, right? So ZI, so they are correlated, right? In this case, the noise is not white anymore. It's called colored noise. Okay, so there's a very easy way to deal with that. I will not cover that in detail, but the thing we're going to do is what? It's whitening. So we can whiten the noise. Okay, so there's a very easy operation here. So basically, we can do the eigenvalue decomposition of the noise, and then multiply all the normal matrices on both sides, and then apply the water filling principle. You can look at the book, but so we don't have time to cover that, and I think that will be okay. Okay, and oh, by the way, so let's say, so everything here talk about is, we can do that over, using capacity formula log half times log 1 plus SNR, right? But in practice for communication, for those of you who have learned communication before, so we know in communication, we do not use Gaussian code word, right? And therefore, it may not be possible to directly use the capacity formula. Although, we can see, okay, we can approximately use it, it is okay. But accurately, we can now say we use a capacity formula. In that case, what should we do? Right? Let's say if we transmit the signal via a constellation, let's do not consider channel coding, right? If we just transmit a signal via a constellation, right? So basically means that in practice, what we do is that we transmit signal. So we transmit complex numbers to a signal, complex numbers. Let's say if we use a QPSK, so we only transmit signal over this 4 position. Okay, then we can now use the capacity formula, right? Because that we need to transmit a Gaussian, right? Then what do? Can we still use the water filling principle? The answer is no, right? Although you can still use it, but it's not optimal anymore. Then somebody solved this problem using a very advanced concept. It's called IMMSE. I denote for mutual information. MMSE is mean square error estimation. Okay, it's another technique in information theory. So we can develop another water filling algorithm. It's called Mercury water filling. We can make it practical, so it's not a problem. Okay, so next, let's start talking about interesting. Okay, quantization. Okay, so now we start talking about chapter 10. Okay, so yeah, that's the last topic in our class. Okay, so we don't have the time to go over all the details here, but we may just cover a part of it. Okay, and our next homework will be a short one. Okay, so it will not be a very long homework. Okay, so yeah, I think all of you should have heard quantization, right? So basically, it means that, okay, so now we have, yeah, it means that I need to do a lot of denoising in my video. So that will be tedious. So basically, it means that we have let's say we have a real number, x, okay? And then we're going to map this number to some, numbers, okay? So that, okay, first of all, we consider scalar quantization. So for the scalar quantization, it basically means that we only want to quantize one number, right? So it has to be from continuous to discrete, right? So, I mean, that's normally what we do, right? So the reason we can, do compression here is that, so we have some distribution of the source information x as what we did in the lossless compression, okay? So scalar quantization is called SQ, and later we're going to see vector quantization, so that's VQ. Okay, for the scalar quantization case, so basically the problem that we're considering is as follows. So we're going to have a real line here, right? So let's say, for simplicity, let's say the range of x is limited. So we have from -a to a, right? So now we need to determine two things, right? So I want to determine how many levels do we want to quantize x, right? So for example, let's say, we may have an interval I1 here, and interval I2 here, interval I3, and so on. Maybe we have interval IQ here. Let's say the total number of quantization level is Q. Okay? So this is the first thing we need to determine, right? How many number of, so what is the Q here, right? So how many number of levels we want, okay? And the other thing is that, okay, so now we know if x is in this range, so we're going to use a number in this range to represent x, okay? And then we need to determine, so what is the number here, okay? So maybe a reasonable choice is here, we just pick the mid value here, x1. And here is x2, here is x3, and here is xq. But the location of this number has to be picked according to some criteria. Okay, so yeah, this basically means that if x is in interval, then we let the estimate of x or quantized value of x equals to xq. Okay, so this is basically the quantization, right? So that's the same as what you have seen before, right? So any questions so far? Okay. Okay, so now we need to kind of convert it to a kind of information theoretic language. Okay, so this procedure, so let's say, let me think, how can we say it? So we can imagine this procedure as a coding problem. Okay, so in this case, the first one is that we need a code book. Okay, x hat will equals to x1 up to xq. Okay. So this is our code book, and so basically, what we do here is that we partition. Number two is that we partition the interval A into sub-intervals. Okay. So we're going to have Q levels in this interval. And the other thing is that we want some criteria, to determine, how many intervals do we have and where each XQ is, right? So normally the criteria is called the distortion. So we want to make the distortion as small as possible, right? So basically it means that, we want XQ, to be close to all X in this interval, right? So, if it's uniform distribution, probably x1 here would be like the midpoint of this, right? But if it's not uniform distribution, then, we may not know that, okay? So normally what we do is that we're going to minimize the distortion, right? And find how many intervals do we have and where is xi, okay? And the meaningful distortion here, so we can use whatever we want, right? A meaningful distortion here for this problem would be what? The mean square error, okay? So let's say if we define the mean square error like the expectation of x minus x hat, okay, so this is our mean square error. Okay, and maximizing Q, maximize the number of Q and where the X is kind of very difficult, right? So to make our life easier, so we can fix Q first. Okay, let's say, so we know we're gonna quantize it into 128 levels. Okay, and then next problem is to find where the boundary of the intervals and where the X is. Okay, then how to find it? We just need to minimize the mean square error. Right, does that make sense? Okay, yeah, that's how we explain that kind of in an information theoretical way. But now let's see the formal definition. Okay, let's see how can we, we still need to model this as, as an encoding and decoding problem. Okay, so as before. Okay, it's almost identical as before. Remember, so what we did before. Okay, so for source coding problem, so in the very beginning, so how do we define it? Right, we have, so for the discrete memory source, we have a bunch of source symbols, right? And then first, what do we do? Yeah, in the very first coding approach, we use a typicality decoding, right? And then we're going to encode, the source information to the sequences in the typical set, and then we give each sequence an index, right? So basically, it means that we map each source symbol, or or ignore some of those, to a indices. Okay, here we do the same thing. Okay, so we say a Q point scalar quantization function. Okay, so this is a function f, right? So basically, we form the source set. It could be discrete or continuous, right? And then we map it to a bunch of indices here, right? So the number of points here, right? The point here is predetermined, it's q. Okay, so we basically map the source symbol to those sequences from 1 to q. Okay, and those is basically our code word. Okay, very good. And I'll just write and see whether it makes sense or not. So when you define what f is, right? So f is defined by the region of scope quantization, or the decision region. Okay, we'll call that dn, such that, so dn is nothing but x has to be here, and then fx is q. Okay, and for this example, d1 would be this. Okay, and d2 would be this, and so on. Okay, yeah, maybe I need a speaker next time. Okay, and this is the f. Okay, okay, so this is basically the encoding. Okay, so we map each each symbol into indices, right? And each indices represent a code word. Okay, and that is our decoding. Okay, so for the decoding, or in source coding, we call that reconstruction function. Okay, that's G. So normally we use F for encoding, G for decoding, right? So this is a map from 1 up to Q to an X hat. Okay, and X hat is nothing but this is or let me write it this way. So the set of X hat is X1 up to XQ, right? And for each one, so it's in R. Okay, so that's basically the encoding function and decoding function. And next, so what is new here is that, so we need to define what is a distortion metric. Okay, so we have so-called reconstruction criterion okay, or that's the distortion measure. Okay, so you can imagine that it's called D, right, for distortion. Okay, so that is a map from x and x hat to some positive number. Okay, like the mean square error, so that's one example. Okay, and then we define the average distortion as the expectation of dx x hat. Okay, and x hat here is a decoded signal. Okay, so yeah, as in our last example, so let's say if we use the mean square error, if that guy equals to this, okay, and then our D will just equals to this. Okay. Is that clear? Oh, here are definition. So now let's see normally how can we determine the region. Okay, so now we need to determine two things, right? One is the boundary, and the other one is where all the x hat is, right? So determine these two things at the same time might be a bit challenging, right? So normally for this kind of problem, what we do is that, okay, so can you do the follows? Okay, if we fixed all the xq, okay, and then can you give me the optimal boundary? Or if I give you the boundary, fix the boundary, can you give me the optimal xq's? Right, so that's basically how we consider this problem, right? So the first case is that, let's say, let's fix the points here, fix all the xq's here, right? For a given set of reconstruction points x hat. So equals to x1 up to xq, right? They're all fixed, right? Then, so what is the optimal decision region? Let's consider, for example, maybe you consider this distance metric, right? We want x and x hat to be as close as possible, okay? Then, so what is the optimal decision region? Right? So let's say, okay, so here, let's fix x1. Let's say x1 here, x2 here, x3, x4, for example. Let's say all of those are fixed. So can you give me what is the optimal decision region? Right, you should have seen this somehow in our communication class, right? Something very similar, right? So because we consider the minimum mean square error or the distance-based distortion, right? So basically, the optimal you're gonna pick is exactly the middle of this guy, right? So that's the smallest distance, okay? So this corresponding to the minimum distance region, okay? So at least, for some metric that can be optimal, right? So this is also called Voronoi region. So it's purely distance-based, okay? So this basically means that, okay, so give you a bunch of points, you can determine what is the optimal region, right? That's not very hard, right? Okay, next. So, okay, so now let's say if the regions are fixed, right? for a given, no, we're out of time already. The decision region. Yeah, let me write down the sentence. Let's say we have I1 to IQ, right? And then, can you tell me how do you determine what are the optimal XQs? Right, think about that. Are what? Yes?
Is it not the same as before? It'd just be the midpoint of the region or the interval?
Not really. So the reason is that we need to consider the distribution of x. It may not be the optimal. Right? For example, let's say if we have a higher probability around here, and then the region may be closer to that.
So it would be the expectation of the interval.
I mean that's here, and then x will be closer to that. Yeah, exactly. Yeah. Very good. So basically, that's so we're doing mean square error estimation, right? So now you may think, if we want to determine the region using the mean square error estimation, so it corresponding to the smallest distance, right? But if we do the same thing for this guy, so we don't know that, we'll just write it, right? So that's corresponding to this guy. The mean square error estimation, so that's basically we want to estimate x, but we know where x is, right? Given x is in this region, IQ, and then we're good. Okay, so now we need to compute that, right? So you can check the way to compute this formula is as follows. In the integral over IQ, we have x px, where px is either the PDF or, if we write integral, it has to be the PDF, right? And then q px dx, right? But if this integral means the back integral instead of Riemann integral, and then it could be both sum and integral. Okay, but this is a point, right? So so we have a name for it, right? It's called what? The centroid of I. The centroid of IQ. Okay, so basically we just need to compute the centroid of IQ, yeah, which is the center of the mass. Okay, very good. And from here, so this basically means that if we know the boundary, if we know the point, then we can compute the boundary. And if we know the boundary, we can compute where the point is. Therefore, if you want to design them both at the same time, you basically, from here we can run an algorithm, right? So we basically can, firstly, we can distribute all the x's uniformly, and then determine the best boundary, and then fix the boundary, redistribute x again, and so on, right? So there's an iterative algorithm. So this is called the Lloyd algorithm. Okay, so it's an iterative algorithm that will converge to the optimal point. Converges to the local optimum. Okay, the reason we call that local is that we cannot guarantee it will give it exactly optimal, right? But it will converge. Okay, that makes sense? Yeah, so let's continue in the next lecture. So we'll talk about vector quantization. Okay, great.